Hi everyone, and to our lecturer Dr. Nudin. So I am Muhammad Ahmed Ashraf bin Abdul Qadir, and my matrix number is 215703, and I'm from Bachelor of Chemical Engineering in UPM. So I'm gonna present about the fundamental principle of thermodynamics, first and second law of thermodynamics. So next, I've divided the context with 5 parts. The first one is introduction. Second is the first law of thermodynamics. The third one is the second law of thermodynamics. Next, connections between those two laws. And finally, as usual, the conclusions. Okay, so next, first, the introduction to our experiment. So, what is thermodynamics? Thermodynamics is a branch of physics that deals with the relationship between heat, work, and energy. It explores how energy is transferred, converted, and stored in various systems. So there are plenty of thermodynamics laws, but we're going to just cover two of them, the first and the second one. The first law of thermodynamics states that the total energy in an isolated system remains constant over time. This means that the energy can be transferred from one form to another, but it cannot be destroyed nor created. And next, the second law of thermodynamics states that entropy of an isolated system is always increasing over time. Meanwhile, entropy is a measure of the disorder or randomness of a system. This means that natural processes tend to move towards a state of greater disorder. These two laws are the fundamental to our understanding the behavior of energy in our universe. Yes, before we start any further, I would like to explain some key points to this video. The first one is energy. Energy is the ability to do work. It exists in various forms, including thermal, mechanical, chemical, electrical, and many more. The ones we usually heard or comment are kinetic and potential energy. Meanwhile, entropy is a measure of the unavailable energy. Entropy is a measure of unavailable energy in a closed thermodynamic system that is also usually considered to be a measure of the system's disorder. That is a property of the system state, and that varies directly with any reversible changes in heat system, and it is also inversely with the temperature of the system. So the first law of thermodynamics, which states that energy cannot be created nor destroyed, but it can be transformed from one form to another. The total energy of an isolated system remains constant over time. This principle, also known as the law of conservation of energy, holds true for all physical processes. So as you can see the image right here on the right part of the slide, it is an example by Newton called the Newton's cradle. Once the balls are given energy, they will just keep bouncing off each other. Why? Because the energy in the system remains constant, meaning that it does not decrease nor increase. But in real life, of course, there's this thing called air resistance, which will make the system go down because the energy is going to be used to resist the air. The ball will keep moving until the energy all be used up. So next, I'm going to give a little example. This example clearly demonstrates the principle of conservation of energy. The ball bouncing and repeating. The total mechanical energy, which is the sum of potential and kinetic of the ball, will remain constant throughout the entire process, even though it changes from from potential to kinetic. So for the potential energy, it is when the ball is above the ground. It it has the potential energy inside it due to its position. The higher the position, the higher the potential energy it holds. So next, it will convert to kinetic energy, as when it is dropping, the potential energy will decrease, while the kinetic energy is increasing because the ball is starting to moving and it has the velocity, thus the kinetic energy. And as the ball falling, when it touches the ground, it will be converted back to potential energy because because the potential and because when it compress, velocity will be reduced and it will starting to bounce off and the process repeated. So we for the first law of thermodynamics, we have this equation which is the delta E equals to Q minus W. Delta E meaning the net change in total energy, Q meaning the heat added to the system, and W meaning work done by the system. The second equation is delta E system equals to energy in minus energy out, meaning that the total energy of a system is equals to the energy going in minus the net change of the energy in the system going out. So let's consider the process of cooking an egg on the stove top. The energy transformation is when heat is transferred from the stove top to the pan and the egg, causing the internal energy to increase. So applying the equation, delta E equals to Q minus W. Delta E is the energy of the system. Energy of the system increases as the egg cooks, which is positive, and the Q is the heat transferred into the system from the stove top, but also transferred out of the system, negative, due to the evaporation. And finally, the W is the work done on the egg by the heat due to its changes in state, which is negative. Therefore, the total change in internal energy of the system, which is the egg and the pan, is the sum of the heat transferred in and the work done. So next, the total energy of a system, which is delta E equals to delta U plus delta KE plus delta PE. The U meaning the change in internal energy, delta KE meaning the change in kinetic energy, and delta PE meaning the change in potential energy. I would like to also I've given the formulas for each energy. So as you can see the three equations here, but I'm not gonna present deeper into that. So moving on, I would like to state an example for this. Imagine a stationary object. What will its total energy be? From the word stationary, we know that it is not moving, and by not moving, it means that the velocity of the object is zero. Thus, the kinetic energy will be zero. Also, by the meaning stationary, it means that it does not move, so it just remain on the ground level. So the potential energy will be zero. So finally, we only got the internal energy. So the total energy of the object is only the internal energy. So next, about the applications, we got three different types of application for the first law of thermodynamics, which is the heat. Firstly is the heat engines. The devices convert heat into mechanical energy. They operate by using a working fluid that undergoes a cycle of expansion, compression, and heat exchange. The first law governs the efficiency of those engines, with the idle efficiency limited by the Carnot cycle. Next, the application is the refrigerators. These devices use the first law in inverse to transfer heat from cold space to warm space. It requires work input to achieve this, and the efficiency is measured by the coefficient of performance. And finally, the application for this is the power plants. In thermal power plants, the chemical energy in coal is converted into thermal energy, which heats the water turning into its high pressure steam. The steam is then used to rotate turbines, transforming thermal energy into mechanical energy, and that energy is going to convert into electrical energy. So next, we have the second law of thermodynamics. It states that the overall entropy of an isolated system, like the universe, always increases or stays the same. It's like a universal law dictating the directionality of time, where we move only forward towards increasing disorder, never the other way around. So You can imagine a perfectly organized sandcastle. It was tall and walls smooth, but leave it untouched for a while, and what happens? It begins to crumble, its structure gradually dissolving into a pile of sand. This is the impact of the second law in action, the tendency of systems to move from order to disorder, from a state of low entropy to a state of high entropy, represented by the symbol S, and higher entropy indicates higher disorder. So we have this equation here. Just the entropy change in universe equals to entropy change of the system plus entropy change of the surrounding. And the right side, as you can see, the graph of entropy, it is always increasing, never decreasing. So next, I'm going to explain about the irreversible process. It is the process that cannot be reversed without external intervention. The second law and irreversibility are linked. It's connected. Natural processes tend to be irreversible, contributing to the unidirectional flow of time. So, to make you understand, think of a room filled with scattered toys. The more spread out and missile the toys are, the higher entropy of the room. This is the impact of entropy. It quantifies the degree of disorder within the system. The second law states that the overall entropy of an isolated system, like the universe, always increases or stays the same. It's like a universal law detecting that we only move forward towards increasing the order, never the other way around. So next, the Carnot cycle. It is a theoretical cycle that describes the maximum theoretical efficiency of a heat engine. It consists of 4 reversible isothermal and adiabatic processes. By studying this ideal cycle, we can gain insights into the limitation of real heat engines. The second law has profound implications for our world. It tells us that no machine can be perfectly efficient, and there are limits to how much energy we can extract from one source. This understanding helps us design more efficient technologies and explore renewable energy options. The Carnot cycle is of course still a theoretical model, but it provides valuable insights into the limitations of real heat engines. By studying this ideal cycle, we can strive to develop engines that approach its efficiency, minimizing energy waste and maximizing the use of resources. So as you can see, we have four parts of Carnot cycle. The first one is isothermal expansion, which is when the gas absorbs heat from a high temperature reservoir while expanding isothermally. Throughout this stage, the gas maintains a constant temperature by transferring heat into work, expanding and performing mechanical work on the surroundings. Next is the adiabatic expansion. The gas continues to expand without any heat exchange with the surrounding, which is the adiabatic process. During this stage, the gas performs work while its temperature decreases due to the expansion, experiencing a drop in internal energy. The third one is isothermal compression. The gas is now in contact with the low temperature reservoir and while undergoes compression while measuring the heat isothermally. As the gas is compressed, work is done in it and it releases heat to the surrounding, maintaining a constant temperature. So finally, the isothermal compression, the gas undergoes the compression without any heat exchange, returning to its initial stage. Throughout this stage, the gas is compressed, performing work onto the surrounding, and the temperature rises due to the compression, increasing the internal energy also. So next, the application of the second law of thermodynamics. First is heat flows. Example is when cooking, like I mentioned earlier. When you cook food, heat flows from the stove top to the food, causing the food to cook. The second law ensures that the heat flow is irreversible. You can cook food by taking heat away from it, right? So next one is energy consumption. And light bulbs. When you turn on a light bulb, electrical energy is converted to light and heat. The second law explains that some energy is always lost as heat energy. making all light bulbs inherently inefficient. I mean, no light bulbs is 100% right. So finally is the refrigeration and air conditioning. This, these appliances use the principle of the second law to remove heat from their interiors, keeping food and other items cool. The second law dictates that this process requires work input, which is electricity, to move heat to its natural tendency. So for the fourth part, which is the connections between the first and second law. The first one is energy transformations and entropy increase. The first law states that energy is conserved in unequal systems. This means the total energy before and after a transformation remains constant. However, the second law tells us that during these transformations, the entropy is always increasing. This implies that while energy can change form, some portion of it becomes less usable or dispersed, contributing to the overall increase in disorder. Next is irreversibility and efficiency. The second law tells us that certain processes are irreversible, meaning they cannot be reversed without external intervention. This is closely linked to the concept of efficiency. No engine or process can be perfectly efficient, as some energy is always lost as waste heat due to the entropy increase. The first law ensures that the total energy remains constant, but the second law explains why we cannot perfectly utilize all available energy. The third one is the directionality of time. Both laws contribute to our understanding of time's arrow. The first law tells us that time is unidirectional because it precedes effect, and energy flow always has a direction. The second law reinforces this concept by stating that entropy increases over time, indicating a progression from order towards disorder. And next is the limitations on energy utilization. The first law ensures that energy cannot be created nor destroyed, while the second law tells us it tends to disperse and become less usable over time. This combination sets limitations on how we can utilize energy resources and design efficient technologies. Understanding the limitations is crucial for developing sustainable solutions for energy production and also consumption. Finally, applications and implications. Both laws have wide-ranging applications in various fields like physics, chemistry, and engineering, and even cosmology. Understanding their connections help us explaining the phenomena like heat flow, chemical reactions, and the evolution of the universe. It also informs the development of technologies that comply with these fundamental principles, like heat engines, refrigerators, and energy storage systems, like I mentioned earlier. So finally, in the last part, conclusion. In summary, the first and second laws, while distinct in their focus, are intricately connected. The first law provides the framework for energy conservation, while the second law adds the layer of directionality and the tendency towards increased disorder. Together, they offer a comprehensive understanding of the universe energy dynamics and guide our advanced, advanced, I'm sorry, advancement in science, technology, and our relationship with the environment. So these are my references for this presentation. So as you can see, I've gathered the information from these links I gave. So that's it. That's all from me. Thank you very much. Sorry for taking too much time. Hope you will consider that. Thank you.